So velocity time graphs are, I think, some of the trickiest graphs that we do in our kinematics graphing unit. So velocity time graph is going to show the object's velocity on the y-axis as a function of time. So the independent, the horizontal axis is time going by. The thing that depends on time is velocity. The first thing we're going to look at is what does the slope of that velocity time graph represent. So a slope is a rise over run. So let's see what the rise is. The rise would be a change in velocity, right? As you go up, your velocity is changing. So that's a delta V. The run is a change in time, right? That's what's on that axis. If I think about, well, what is a delta V over delta T? That's actually just the formula for acceleration. So the slope actually must represent the acceleration. So slope of a VT graph, a velocity time graph, is equal to the acceleration of the object. All right, let's look at a few velocity time graphs and get a sense for how this all works out then. So here's some straightforward ones. You've just horizontal lines on your velocity time graph first. All right, so this first one here, we have velocity on the y-axis, time on the horizontal axis, and what I have is a positive horizontal line for my velocity. So in this case, it's actually at the number 3, if I count up 1, 2, 3, at least ticks anyway. So that means I have a velocity of 3 meters per second, and it's constant. It's a positive velocity, which means I'm moving forward. So this is positive velocity is moving forward. So forward motion. And notice how the velocity is not changing. It's a horizontal line here. So that's at constant speed. Constant speed, constant velocity forward. All right. The acceleration here is the slope of that line. Notice the line is horizontal, so the slope is 0. There's no acceleration here. It's constant speed. You're not speeding up, not slowing down. All right, the next one, we've got a negative horizontal line. That just means you're moving backwards. So it's backward motion. And you're moving backwards at constant speed. And horizontal line, no slope, so that has 0 acceleration. This one is a horizontal line of the velocity at 0. So that means you're just stopped. The velocity is constantly stopped. So that object is stopped, and so of course it also has 0 acceleration. What people find tricky, I find, with velocity time graphs is they see a horizontal line and they assume it means stopped. It only means stopped if that horizontal line is at 0 velocity. If that horizontal line is, say, at some negative velocity, it means constant speed backwards. All right, let's get into some trickier ones. Let's say we have a sloped line on a velocity time graph, so maybe something like this. What we see here is we're starting out at 0 velocity right here, so that's 0 velocity, and we're reaching some positive velocity value forward. So if we started out stopped, and then we get faster and faster and faster forward, what we're doing is speeding up in the forwards direction. So we're moving forward, and we are speeding up. In this case, the acceleration is positive. You can see that that has a positive slope. Also, speeding up in the forwards direction, that's going to be a positive acceleration. Here's one, it's a bit trickier. You start out with a negative velocity, so that means you start out moving backwards, quite quickly moving backwards. But then as time goes on, your velocity gets less and less negative until you end up stopped. So that means you're moving backward, but slowing down. So moving backward, it's slowing down. The acceleration here is still positive. So moving backwards, slowing down, still has a positive slope for the acceleration. Look at two that have negative accelerations next. This one, you start out moving forwards at a positive velocity, so it's a fast positive speed, and you go slower and slower and slower until eventually you stop. So this is moving forward and slowing down. And the acceleration here is negative, right? We're getting slower while moving forward, or you can look at the slope of that line, it's a negative slope. So negative acceleration. Here, you start out stopped, but then you get faster and faster in the backwards direction. So this is moving backward and speeding up. Speeding up backwards. The acceleration here is negative. You can see that has a negative slope, and speeding up in the backwards direction is a negative acceleration. So just to help you keep track of those different scenarios where you have a sloped line on your VT graph, if you're dealing with a velocity time graph where the line is pointing away from 0, so that's, here's V, here's T, so that's either this case or this case, right? The lines are pointing away from 0, then that object is speeding up. Because 0 is stopped, so going away from 0 is speeding up, either speeding up forwards or speeding up backwards. If you see the lines pointing towards 0 as time goes on, so that would be like this. Here's V and T. This situation or this situation, 0 is stopped, right? So you're starting out fast here and getting slower and stopping, or starting out fast backwards here, getting slower and stopping. So in both of those cases, if the lines are going towards 0, your object is slowing down. All right, that's our first bit for a velocity time graph. So the slope represents our acceleration. We can actually also learn something from the area under a velocity time graph. And by the area under the velocity time graph, I mean this. Look at the line you have on the velocity time graph. Say it's just a constant velocity here. Go straight down to the time axis and look at all the area between your line and the time axis. So that area right there. I'm going to try and figure out what that area means. And we're going to do that using our equation for velocity. So average velocity is displacement over time. If I rearrange this equation, I could multiply both sides by time. That would cancel time off the bottom here. And I'll get displacement is velocity multiplied by time. Let's look a little bit closer at this area. If I wanted to calculate the area of this rectangle, I would take the velocity on this side, and I would take the time on this side, right, the delta t here. So velocity multiplied by time would give me that area there, right? This is a rectangle, so it's just length times width here. So velocity times time gives me that area. That means that the area under a VT graph represents the displacement. So my velocity multiplied by my time, velocity by time is the area, that gives me displacement here, right? So that area must be the displacement. And that will work for even more interesting velocity lines where it's like not a horizontal line, like an angled line. We can still use that rule. Just a few notes about calculating the area under a velocity time graph. Make sure you're always measuring the area between the line and the time axis. So what I mean is this. If you have this velocity time graph here, maybe your velocity looks something like this, some sort of slanted line up there. You want to find the area all the way down from your velocity line, all the way down to the time axis, that whole area in there. In this case, that area is above the time axis. If you see an area that's above the time axis, that's a positive or a forward, missed part of the word, or a forward displacement. And if you see an area below the time axis, that's actually moving backwards. So that would look like this. Here's V, here's T, maybe our velocity is something like this. that right there. Our area is going to be the area between that line, and now in this case up to the time axis. So it's this area in here. So that is an area below your time axis. Go from the time axis down to your velocity line. That means you're moving backwards. So that's a negative displacement or backward displacement. All right, let's actually do some of these with a graph. So here's our first example. I want to find the acceleration over each section and the displacement over each section. So I'm going to start with acceleration here. For the first section, so that's 0 to 2, my acceleration is always the slope, right? So I'm going to be finding slopes here. The slope for this section here is going to be the rise over the run. So A is going to be my delta V, my rise, over my run, delta T. That is equal to my change in velocity from 1 to 2 is 2 minus 1, or 1. My change in time from 0 to 2 is 2. So I get a half. So A is a half. And the units of A are meters per second squared. Okay, the displacement over that same interval is from 1 to 2 is this whole area here, that area right there. So calculating that area, I have a rectangle on the bottom, and then I have a little triangle here. So we're going to find the area of each one and then add them together. So displacements are areas on a velocity time graph. The area of the little rectangle, so delta D, is going to be this rectangle on the bottom, which is 1 times 2. So that's 2, plus the area of our little triangle here, which is base times height over 2. So that's 2 times 1 divided by 2. So 2 times 1 divided by 2. So that makes 2 plus 1, or 3 meters. So the displacement over that time from 0 to 2 seconds is 3 meters, and it's in the forward direction because it's a positive area. Great. From 2 to 3 seconds, my acceleration is going to be the slope. The slope of this line is 0, right? This isn't moving up or down. So acceleration is just 0 meters per second squared. But I'm actually still going somewhere, so I still cover ground. That's because I'm moving at a constant velocity. I'm not stopped for this section. I'm moving forward at 2 meters per second over that section. So my area is going to be the area under the line here, this area right here. That area, it looks like a little rectangle. Base is 1, height is 2. So the area is my displacement. It's going to be base times height, which is 2 meters. Still forward because it's a positive area. All right, last section. The acceleration over this section here from 3 to 4 seconds. A is my change in velocity over my change in time. My change in velocity goes from 2 down to 0. So if I could write this out as V2 minus V1 over T2 minus T1. Sometimes that helps people a little bit just to make sure they get the sign right. My V2, the final velocity I get to here is 0. My V1 starts out at 2. So that's 0 minus 2. On the bottom, T2 minus T1, I start at 3 seconds, I go to 4 seconds. So that's 4 minus 3. And that makes negative 2 over 1, or negative 2 meters per second squared. The area is a little triangle here. That area right there. So delta D, it's a triangle, so it's going to be base times height divided by 2. The base is just 1 unit long here, so it's 1, and the height is 2, so that's going to be 1 times 2 over 2, which is 1 meter, and it's still forward because it's a positive area above the time axis. So all of those displacements are forward. So I ran out of time there. I ran out of space there. Okay, My total displacement means I just get to add up all my displacements. I move forward 3 meters, then I move forward another 2 meters, and then I move forward 1 meter. So it's going to be 3 meters plus another 2 meters plus another 1 meter, which makes 6 meters forward altogether. All right, our next example has some moving backwards in it as well. So for our first section, we're moving backwards at a constant speed of -2. Then we're going to be slowing down, still moving backward. Then we start moving forward and we speed up. So if I look at this first section here, I'm going to figure out my slope. Accelerations are slope. That's just a horizontal line, so my slope is 0. Acceleration is 0 meters per second over that, meters per second squared, over that section. The area is my displacement, so I do cover ground even though I'm not accelerating because I am moving at a constant velocity. So that area right there, it's going to be a negative area, so it's my displacement. So it'll be negative, and that's because it's below the line. The area, it's a rectangle, so it's going to be just length times width. Length is 2, width is also 2, so I get -4 meters. Or I could phrase it as 4 meters backwards. I'll just write backwards on the side so you remember that it's moving backward. All right, next section here, my acceleration is positive, right? That's a positive slope. Even though I'm moving backward, it's a positive acceleration because I'm slowing down in the backwards direction. Acceleration is going to be v2 minus v1 over t2 minus t1, which is our v2, we reach 0 meters per second right here, that's 0. And I start at -2, so minus a -2 divided by my t2 is 3, my t1 is 2. So that means on the top I have +2 over on the bottom 1. So that gives me 2 meters per second squared for my acceleration. The area of that section here, so that's going to be this area right here, is a triangle. So that delta D is going to be base times height over 2. So base is 1 times the height is 2, all divided by 2, and it's a negative area because it's below the time axis. So that gives me -1 meter, and it's backward. That's what the negative means. Oh, backward. There we go. All right, last section. I need the slope of this line right here. So I start with a velocity of 0, I move up to a velocity of 4. So if my acceleration is v2 minus v1 over t2 minus t1, v2 will be the 4 meters per second I get to, v1 is 0. On the bottom, time starts at 3 and goes to 4 seconds. So it'll be 4 for t2 minus 3. So it gives me 4 minus 0 over 1, which is 4. So the acceleration there is just 4 meters per second squared. And the area of that piece is finally a forwards piece. We have a triangle here, a base of 1, a height of 4. So delta D is going to be 1 times 4 over 2, base times height over 2. And that gives me 2 meters in the forward direction. So when I want to find my total displacement, what I have to do is just add up all these values. So add up the -4 meters plus the -1 meter plus +2 meters, which gives me overall -3 meters. So that's overall I move backwards 3 meters is my total displacement. And that's it.